So now we're ready to start talking about the most important of the carbon homocycles, cyclohexane. And I think where I want to begin is just by showing you a model of cyclohexane and how its Newman projection is going to look quite different from everything else that we've seen. So when we look at cyclohexane, you might be inclined to think that cyclohexane is two-dimensional. In fact, it's three-dimensional. And when we do the Newman projection, we want to look down two bond axes simultaneously. So imagine this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. I'm going to look down the C3, C2 bond axis and the C5, C6 bond axis. And if you look down C3, C2, you see a very nice gauche conformation. Same will be present between C5 and C6. So there's less torsional strain with cyclohexane than any other carbon homocycle. Less than cyclopentane, less than cyclobutane, less than cyclopropane. So one of the things we want to do first is to be able to draw a Newman projection of cyclohexane. Notice that when I look at this as though it's two-dimensional, you see two different kinds of hydrogens. You see hydrogens that either come straight out of the plane of the screen towards you or are in the screen away from you, or you see hydrogens that come towards you or away from you at an angle. And so if I rotate this molecule such that it has a central equator or a central plane, there are three that will poke straight up and three that will poke straight down on the axis of the molecule, and we call those hydrogens axial. And there will also be six that go along the equator of the molecule, and we'll call those six equatorial. So as we begin to draw this molecule, the artistry of drawing cyclohexane is one that needs a lot of careful practice in order to master it. So notice that this is called the chair conformation. And I want to highlight the six atoms that comprise this six-membered ring. We see the head of the chair, the foot of the chair, and the seat of the chair. And I want to very lightly grid in this plane that helps us define what is axial and what is equatorial. So the axial groups will be 90 degrees to this imaginary plane. And so we'll either go straight up or straight down. Straight up, straight down, straight up, straight down, straight up, straight down. I actually want to put those in a different color. Put them in yellow. These are the axial substituents. And I'm going to label these hydrogens as H sub A. The A is for axial. And then at each position, there's also an equatorial. And I'm going to render the equatorials in cyan. And we really want to draw these parallel to the opposite line. So this is equatorial. This bond is parallel to this bond. 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 And there's a couple that are a bit more difficult to draw. And I'm going to place these like so. So 6 equatorial positions and 6 axial positions. What we want to do is re-emphasize and number our carbons. And then we're going to draw a Newman projection. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. And we want to look down the C3, C2 axis. So we're going to have our I right here. And the C5, C6 axis. And so we're going to have our I right here. C5, C6, C3, C2. And that circle's way too big. Let me fix that. Above the plane, we're going to see C1. So C1 is bonded to C2 and C6, which are the larger circles. C4 is bonded to C5 and C3, which are rendered by the dots. Of course, both of these are methylene carbons. And everything else is going to be a hydrogen. And notice that unlike in all of the other carbon homocycles that we've studied, if you ignore the methylene hydrogens above and below, all of these other hydrogens are going to be gauche one to another. And that's the most stable conformational relationship you can have amongst all of these hydrogens that I'm going to shade in green. And so this is the Newman projection of the most stable conformation of cyclohexane, a conformation that we refer to as the chair conformation. Now there is another important conformation of cyclohexane. It is much higher in energy, and we call this conformation the boat conformation. So I want to first start by drawing the plane. Again, carbon 2, carbon 3, carbon 5, carbon 6. Carbon 4, pretend this is above the plane. So here's the plane of my molecules, and I probably need to convince you with a better picture that both C6 and C4 are above the plane. It's kind of difficult to do. So I guess we can do something like this. Carbon 1, 2, 3, 4, 5, and 6. And if I look down carbons 3 and 2 and 5 and 6 simultaneously, 5 and 6, 3 and 2, I'm going to see something like this, and it's quite different conformationally. Of course, everything else will be a hydrogen. And you should immediately begin to see the problem. All of my hydrogens are going to be eclipsed, much higher in energy, as we've already discovered from previous podcasts. This is the boat conformation. Chair conformation, lower in energy than the boat. So we can now start taking a look at some of our PowerPoint slides. If we start on slide number 32, you can see the chair conformation pretty clearly. Head of the chair, foot of the chair, seat of the chair. We're going to look down 3, 2, and 5, 6 simultaneously. So we're numbering this 1, 2, 3, 4, 5, 6. When we look down those bonds, this is the resulting Newman projection. Really got to see this by building a plastic model to see it appropriately. The boat conformation, again, when we look at the Newman projection, everything is going to be eclipsed. This will introduce a tremendous amount of torsional strain. We will not have that nice overlap between the bonding MO and the anti-bonding MO of adjacent carbons, as we saw in our last podcast. And here is a potential energy diagram of the conformations of cyclohexane. Notice that there are 2 chair conformations. This chair can actually undergo what we call a ring flip, such that the head that's to the right becomes the head that's to the left. The foot that's to the left becomes the foot that's to the right. And there are several intermediates in this flipping phase. So the half chair is the global maximum. The twist boat is a global minimum. The boat is a local maximum. And notice the energy differences are pretty substantial. So the chair conformations are going to be favored by several kJ per mole. Klein also takes you through a nice primer of how to draw these. Practice this a lot so that you do it right. Because if you draw something like this, it is going to be wrong. And so you're just going to take a lot of practice. I would also put your axial groups in one color and your equatorial groups in yet a different color. Just helps alleviate confusion. Now let's talk about what happens during a flip. But before we get there, let's actually look at an animation of a ring flip. Notice on this slide that I have an axial substituent, but after the ring flip, it becomes an equatorial substituent. What I would like to do now is to convince you that this is actually what happens. And so in the ring flip, first of all, we're going to get the half chair conformation, as we do right here. Make this a little bit bigger. If we continue, We're going to get the boat conformation, then a twist boat, and then finally the chair flip. I want you to notice very carefully what just happened. If we go back to the starting structure, the blue hydrogens are axial and the red hydrogens are equatorial. After the ring flip, half chair, twist boat, full boat, twist boat, and finally the other chair conformation. Notice that the axials that were blue are now equatorials, and the equatorials that were red are now axials. Of course, if we allow more energy to be input into the system, we're going to find that we're going to get the original structure back. Half chair, twist boat, full boat, other twist boat, other half chair, and the other chair conformation. And the axials are now once again blue and the equatorials are once again red. One of the interesting aspects of this, and it's now appropriate for us to discuss this because we've looked at NMR spectroscopy, we might expect that all of the blue hydrogens should give one NMR signal and the red hydrogens should give a second. But because these readily interconvert at room temperature, the NMR spectrum will only show one signal. In order to get two signals, we'd have to have very, very cool conditions, those approaching absolute zero, and then we would see two signals. So even though there are two distinct signals between equatorial and axial, we can't distinguish them at a normal room temp NMR experiment. Now this is going to become significant because when I have a bigger substituent than hydrogen, one that's going to give more significant torsional strain, we're going to find that when that substituent is in the equatorial position, it's going to be more energetically favorable. And that really is going to be the point of our next and really last podcast on this material for the conformational analysis chapter, where we begin to look at different substituent effects of di-substituted cyclohexanes. And so we'll start with the classic examples of 1,2-cis, 1,2-trans, which is more stable in Y, 1,3-cis, 1,3-trans, which is more stable in Y, 1,4-cis, 1,4-trans, which is more stable and Y. So I'm going to stop this podcast and then we will pick up with the chair flip. Again, as a reference on 437, the cyclohexane conformation to the right is more stable than the one to the left because of the lack of steric strain, because of the lack of torsional strain. We can convince ourselves of this just real quick. Let's see if we can get T-butyl cyclohexane. And we can. And this T-but cyclohexane is in the equatorial position. This, the atomic dashboard is always going to give us the most energetically favorable. But I want you to imagine this big bulky group right here. You're going to have a significant, what we call 1,3 dipole, a flag dipole interaction, where when this begins to rotate, it is going to clash sterically with these two hydrogens. The bigger and bulkier the group that we put on cyclohexane, the greater the preference will be for the equatorial position. I'd like to convince you of this with one last piece of data. And here we are. Well, there we were. Need to get it back. Here we go. So, first of all, notice the bigger the substituent, the more energetic penalty you're going to pay. And then also notice how much more equatorial than axial you get. So we like to think that chlorine is larger than a methyl group, but it's not. Because first of all, a diaxial interaction with methyl group is 7.6 kJ per mole, but a chlorine only 2 kJ per mole. You do always favor equatorial over axial, but notice you get a pretty substantive amount of axial with chlorine, not so much with methyl cyclohexane. Now compare that to T-butyl. 99.99% is equatorial, and 0.01% is going to be axial. So this data shows very well and very clearly the bigger the substituent, the greater the preference for equatorial and the more energetic the penalty is going to be with the 1,3 diaxial flagpole interactions. We'll pick this up on the very last podcast at which we look at di-substituted cyclohexanes.